Let's talk about some of these questions. The first one says that the central limit theorem says that which of these three things is true. So what if we have a big population of people? Imagine the heights of all people in Concord. We don't know what type of shape that population has. It could be normal like this, or it could be skewed like this. Or it could be skewed to the right, or it could even be skewed to the left. If it follows a normal distribution, it means that most of the people are in here. Most of the people have heights somewhere in the middle. There are fewer people down here with very short heights, and fewer people up here with taller heights. What this shape right here is showing is that if this is true, then most of the people in Concord have short heights down here, and less people have the taller heights. So this is normal, this is skewed. What the central limit theorem says is that if you take well, first of all, if the population follows a normal curve like this, then, and if we take a sample of 30 people, let's say we find 30 people, we take their 30 heights, we add them, and we divide by 30, and we get the mean height. So we get the average of this group of 30 people. That's one average. And then, what if we take, what if we find another sample of 30 people? I mean, what if we're finished with this sample, and then we go out and we get another sample of 30 people? We add up their 30 heights and we divide by 30. And then we find another group of 30 people. And we find their average. And some of our samples of 30 will overlap each other, because we could, if we go out and get 30 people, we might end up with a few of the people that we used last time. Or I mean, a few of the people that we've already used before. So this sample of 30 people could include some of the same people as this sample of 30 people. So right here we have 4 samples of 30 people, and we've calculated the average of each one, but we're just saying that 2 of our samples included some of the same people. We keep doing this for all possible samples of 30 people from in the Concord population. We might get some samples of really tall people out here. This group of 30 people would have a higher average. We might get some samples of 30 people that are shorter. For example, 30 people out here. If we calculated the average of these 30 people, this sample mean would be pretty low, because it's a short group of 30 people. If we calculated the mean height of this group of 30 people, it would be a higher mean, because it's a tall group of 30 people. And these groups of 30 people are more, have more average heights. I mean, they're more in the middle, so their heights are more medium. So these four averages, meaning the average of this, the average of this, the average of this, and the average of this, those four averages will be more medium averages compared to the low average here and the high average up here. So if we calculated all of these means for all combinations of 30 people that could be selected, and we plotted the means in a graph, the means would also follow a normal curve like this. And this would be called a sampling distribution. So this is the population. This is sampling distribution. So each value inside of here was an individual person, but each value in here is the mean of a sample. And I said that this was a taller sample, so this group of 30 people will end up having a mean down toward the low end. This group of 30 people will have a mean toward the bottom end. And like I said, these samples of 30 people will probably be somewhere around here. I'm not sure exactly where they'll be, but somewhere in the middle of the curve. So each of these values that make up the sampling distribution is an average of a sample. This is an average of a sample here. Maybe let's say that this is the average of this sample up here. This is the average of this sample here. This could be the average of this sample, and this could be the average of this sample maybe. But the sample means follow a normal distribution if the population is normal. And also if the population is not completely normal but roughly normal, the sampling distribution will be roughly normal also. But what if the population of people in Concord is skewed? What if the heights are skewed like this, skewed to the right? Well, then if we go into the population and we do the same thing, we find 30 people, we calculate the average height of these 30 people, we calculate the average height of these 30 people right here. Now we have two values, two different means. We find another group of 30, we calculate the average. We have three values now because we've calculated three means. We do this for all possible groups of 30 people, and we keep storing up more and more sample means. And then once we're finished, we take all those sample means and plot them in a histogram. And even though the people were skewed like this, the sample means will still be roughly normal. Because if the sample size is 30 or higher, the sampling distribution is at least roughly normal, just even when the population is skewed. So if the population is skewed, the sampling distribution won't be completely normal, but will be at least roughly normal if the sample size you're using is 30 higher. So if we were doing this with samples of 35 people, we would get a normal shape, or a roughly normal shape. The truth is that the larger the sample size you use, the more and more normal the sampling distribution will be. But 30 is the point where it gets to be about roughly normal. So if population is normal, sampling distribution is normal, this leads to this. Population is skewed. The sampling distribution is at least roughly normal, or is roughly normal when the sample size is at least 30. Like I said, the bigger the sample size we use over here, the more normal the sample means will end up becoming in the sampling distribution. But if you use a sample of 30, that's the sample size that's generally big enough for the samples to be roughly normal. So if the population is normal, the sampling distribution is normal, regardless of what sample size is being used to create the sampling distribution. If the population is skewed, the sampling distribution will be roughly normal for sample sizes of at least 30. So a small sample size, like a sample size of 10, would produce a skewed shape, just like the population. It would be skewed to the right. But a sample size of 30 will be roughly normal. So let's take a look. The central limit theorem says that if you sort a population into all possible samples of 30 people, this is what I was talking about here. You take all possible samples of 30 people and calculate the mean of each one, and then plot those means in a histogram like this. Then calculate the mean of each possible sample of 30 people and create a histogram. The histogram of sample means will be at least roughly normal even when the population is skewed, like it is here. So that's the answer. This one isn't correct because this one is saying that choice number A is saying that if you recruited a sample of 30 people from a skewed population, that those 30 people's heights, the heights of those 30 people, would follow a normal distribution. And that's not correct. If you take 30 people from a skewed population and you created a histogram with the heights of those 30 people, what you have is a histogram of the heights of people inside one specific sample of 30 people. That's not what's going to be normal. What's going to be normal is if you took the means of all different possible samples of 30 people and then plotted each of the means in a histogram, and you have a histogram of means, not a histogram of heights, but a histogram of means. That's what ends up being roughly normal. So it's not C. I mean it's not A. Also, this is saying if you calculate the means of at least 30 samples and create a histogram with those 30 samples, it'll be roughly normal. It's not the number of samples isn't what needs to be 30. It's the sample size that needs to be 30. So if we if we went around and we got 30 people and calculated the average, and we did it again and we calculated the average and we did it again. If we did this 30 times, we would have 30 sample means because we used 30 different samples. We calculated the mean of each one. So we would have 30 sample means. Having 30 sample means isn't what's going to make this normal. What's going to make it normal is the fact that we're using 30 people each time, and each sample has 30 people inside of it. So it's not the number of samples that needs to be 30, it's the number of people inside each sample that needs to be 30. So that's why C isn't correct. It's the sample size that matters, not the number of samples. Question number 2 says, if we did the same thing, if we calculated the means of all possible samples, but with a skewed population, it says skewed to the left, but it doesn't matter if it's skewed to the left or skewed to the right. It just matters that it's skewed and not normal. If we went around and did this with a sample size of 10 and calculated the means of all possible samples of 10 people from a skewed population, the sample size is under 30, which would mean the means of all of those samples would follow a skewed curve. It would look just like the population does. So if the population is skewed to the left, and we're calculating the means of all possible samples of 10 people, those sample means will be skewed to the left, just like the population is, because the sample size is too small. Because each sample is being calculated with only 10 people. That's what I was talking about. Because we're it's not number A because it's, like I said, it's not the number of samples that we're talking about. It's not skewed to the left because we're using 10 different samples. That's not the reason why. The reason why it's skewed to the left is because each sample that we're using only includes 10 people inside of it. Because if we took a skewed population, we take 10 people, we calculate the mean of those 10 people, we add them up and divide by 10, we get a mean. We do it with another group of 10 people, we add their heights and divide by 10, we get a mean. We do it again, we find 10 other people, we add their heights and we divide by 10 to get a mean. Each time we do this, we're doing it with a sample of 10 people. And it's the fact that we're doing it with 10 people each time is what's going to make the samples skewed to the left, just like the population. The fact that there's only 10 people inside each sample we're using is what is going to make it skew to the left. The sample size isn't 30. It's lower than 30. And it's not the number of samples that matters, it's the sample size that matters. Number 3, I made an accident, and I think I wrote out the same question. But what if I had said normal? Normally distributed. And we calculate the means of all possible samples of 10 people at a time. Well, the sampling distribution that we're going to end up creating is normal, will be normal, because, like I said, if the population is normal, the sampling distribution is always normal. It doesn't matter what the sample size is. This says that the heights in a certain population are skewed to the right. Just like in the picture I just drew out. We take a sample of 30 people, we record the heights of those 30 people, we calculate the mean of the sample by adding and dividing by 30. I told you that if the population is skewed to the right, and you take 30 people and record their heights, those 30 recorded heights aren't going to be normal. It's not the 30 heights that you're recording that will be normal. What is going to be normal is the means of the possible samples of 30 people. So it's not the 30 individual people in your sample that are going to be normal. What's going to happen is in this population of people that has that's skewed to the right, meaning it has a lot more shorter people and fewer taller people, there's if we're taking a sample of 30 people, there's many different possible samples of 30 people that could be chosen. Here's a possible sample of 30 people. Here's another possible sample. Here's another possible sample of 30 people. So these are all of the possible samples of 30 people that might be chosen when we're selecting 30 people. So if we're selecting 30 people, we might get this group, we might get this group, we might get this one. Each one is possible. And every possible sample of 30 people that could be chosen has its own mean, has its own sample mean. And for example, this sample of 30 people has its own sample mean. So the means of all of those possible samples follow a normal distribution, at least roughly, because of the sample size of 30. So it's choice B. So, like I said, there's many different possible samples of 30 people that could be chosen from the population. And every possible sample has its own average, its own mean. And all of those different means are just a bunch of different values, and those values follow a normal distribution. What this question is asking is, when can you use the z-table or t-table to calculate the margin of error? It's actually asking you, when can you use either table, meaning in what situation are either of these two tables allowed, and in what situation are neither table allowed to be used. In order for the z-table or t-table to be used, the sample size has to be at least 30, and the means of the possible samples have to at least follow a normal distribution. If that's not the case, if your sample size isn't at least 30, you can't use the z-table or the t-table. So if the possible samples, the sampling distribution, follows a normal curve, or at least roughly, you can use the z-table or t-table. But if the sampling distribution doesn't follow a normal distribution, you can't use the z-table and you can't use the t-table. Both tables have this rule that has to be followed of the samples, of the possible samples, sampling distribution being at least roughly normal. So right here in green, this is the rule that has to be followed. This rule has to be met to use the z-table or the t-table. If this rule right here is not met, you can't use this table and you can't use this table either. The t-table is used when the sample standard deviation is unknown. When the population standard deviation is unknown, only the standard deviation of the sample is known, because the t-score formula, uses the sample standard deviation, the letter S. If the population standard deviation is known, that's when you use the z-table. If the population standard deviation is known, I told you that you would use a z-score, so it has to be A or B. And if the population standard deviation is known, it can be plugged into the formula, and you don't have to use the sample standard deviation. Because if it's known, you just plug it into the formula. So it has to be choice A. The sample standard deviation is only used, this would only be used when the population standard deviation is unknown, and you would use the sample standard deviation and the t-score in that situation. Like I just told you the answer to this. When the population standard deviation is unknown, you use a t-score and sample standard deviation. Because if the population standard deviation is unknown, it can't be plugged into the formula, which means that the sample standard deviation has to be plugged in. Okay. For number 9, it asks what the 95% margin of error is. probably shown you this before, how how you have a normal curve like this. You have the population mean at the center. You have a middle section in here, which is the middle 95% of the sample, and the margin of error is the distance from the population mean to this boundary over here, the upper boundary, and it's also the distance from the population mean to the lower boundary, because this distance is the same as this distance. And what I wanted you to understand for this multiple choice question is that this 95% doesn't mean 95% of a group of people. It's not, we don't have people inside of here. We have possible samples inside of here, the possible samples that could be chosen. So the margin of error is the distance from the population mean to the upper, and to the lower boundaries of the middle 95% of the possible samples that the researcher is drawing from. So 95% of possible samples are in here, not 95% of people. So it's the distance from the population mean to the lower and upper boundaries of the 95% possible samples that might be selected, not the people, which is what choice A says. How do you calculate a 95% confidence interval? Well, first you have to calculate the 95% margin of error, and then you have to calculate the sample mean, and then to get the confidence interval, you take the sample mean, subtract the margin of error, and also take the sample mean and add the margin of error. You do sample mean minus margin of error, and sample mean plus margin of error. It gives you two numbers. The confidence interval goes between those two numbers that you've calculated. It's the space between those two numbers. So it's choice A. You add and subtract. You don't add. You don't multiply and divide like you would here in these choices. 11 through 13 are asking you to actually create a confidence interval one step at a time. Question number 11 is asking you to do the first step, which is calculating a z-score. Well, not calculating it. For confidence interval, you actually look up a z-score in a z-table. And what you do is, I'm telling you that we're working with 95%. We're going to be creating a 95% confidence interval. So what we do is take this percentage I'm giving you, go to the z-table, if we have it here. Here. Go to 95%. 0.95 means 95%. It's 1.96. That's your answer. And it's positive 1.96. What you do now is, when I say what's the distance from the upper end of the 95% to the population mean, what I was talking about is this distance from this upper boundary to the population mean, which is really just the margin of error. So I could have just said what's the margin of error in that question. And to get the margin of error, you would multiply your z-score times, well, I'll show you the formula. I'm telling you that the standard deviation of the population is 6.2. So the population standard deviation is known in this case, because I'm saying that it's known, which means that we have this formula. And the fact that it's known is why we're using the z-score up here. The margin of error with the population standard deviation being known is this. It's z. And in a confidence interval, in the margin of error formula, you'll see an alpha over 2. This is just notation. All this notation is saying is that we're talking about the z-score right here that gives you the margin of error. So it's a specific type of z-score. It's pretty much just the z-score we got from the table times sigma, which is the population standard deviation, over the square root of our sample size. So we know that the z-score we got from the table was 1.96. Let's find out what our standard deviation is. I'm telling you that it's 6.2. And what's our sample size? Well, I'm telling you that there are 30 recorded heights. So the sample size is 30. So its standard deviation is 6.2. Sample size is 30. N is 30. We have to just do these calculations. The square root of 30 is about 5.48. We divide those two numbers. Comes out to about 1.13. Multiply that by our z-score of 1.96. We get about 2.22 rounded. That's our margin of error. So it's choice D. Now what about number 13? This is asking what's the confidence interval. And I'm showing you it in a little bit of a different way. I'm not showing you the final answers for the confidence interval. If I did show you the final answers, it would just say this number to this number. Instead, I'm showing you the sample mean plus or minus the margin of error. So think of it as kind of like an unfinished version of the confidence interval. We have to find out what the sample mean is, which would mean that we would have to add these 30 numbers and divide by 30. And let me see what the answer would come out to. 20, 25, 30, 35, 40, 45. I can already tell that the answer is, the sample mean is 32.5. That's what you get if you added these and divided by 30. The way I was able to get it is by, well, I know that 20, 25, and 30 are the bottom half, and 35, 40, and 45 are the top half. So I just took the number halfway between 30 and 35. That's a shortcut I could use in this situation, but it might be easier for you if you just added them and divided by 30 to make sure you get the correct answer. So it's 32.5, and that's the sample mean, plus or minus the margin of error that we got in question 12. So it's D. So this was a series of questions in which you had to get the z-score first from the table, use it to calculate the margin of error, and then use the margin of error to get the confidence interval. 14, 15, and 16 are another series of questions just like 11 to 13. The only difference is you're going to be creating an 80% confidence interval, which means we would go to the table, we would go to 80%, we would get the number from the table, you would take that z-score, plug it into the margin of error formula, which I showed you here, to get the margin of error. You would then calculate the sample mean, add these 30 numbers and divide by 30. Then you would get the sample mean, and it would be sample mean plus or minus whatever margin of error you found in question 15. I think I'm not going to give you the answers to these because I think you can just follow the steps and use these questions to get some practice on your own. So I shouldn't give away the answers. Okay. What this question is getting at is, let's go to the table for 80%, which is 0.80. It says z is negative 1.28. What that's saying is that if you have a normal curve like this, if the sampling distribution follows a normal curve, then 80% of the possible samples are between these two z-scores. Negative 1.28, the negative version of the number from the table, and 1.28. What this is asking is, if a table says that these are the two z-scores at the outer edges of the 80%, and when we did our example in class, when we made the 10 possible samples like this, I think it looked something like this. We calculated the z-score of sample 2, and we calculated the z-score of sample 9. Because, remember, it was between these two x's was 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 10. So this was the middle 80% of the possible samples. We calculated the z-score at this boundary. We also calculated the z-score at this boundary. we calculated the z-score of sample 2 and the z-score of sample 9 right here. And these two boundary z-scores didn't come out to negative 1.28 and 1.28. I think when we did them, they came out to maybe negative 0.8 and positive 0.8. So they didn't match these numbers. The reason why is because the possible samples that we created in our sampling distribution right here didn't follow a normal curve. If you draw a curve around this sampling distribution that we created, it doesn't really follow a bell curve. So these two numbers right here are the boundary z-scores of the 80% only when the sampling distribution follows a normal curve. If the sampling distribution doesn't follow a normal curve, these won't be the boundary z-scores anymore. So the 10 possible samples that we created in that example did not follow a normal distribution. They followed kind of this flattened out type of shape. So this one says, we randomly selected 30 people from a large population. We have recorded the heights of those 30 people. These were the heights that we recorded. It's saying if the sample of 30 people is in the lower tail, then what happens to the confidence interval? Well, whenever you get an extreme sample from the tails, like a sample out here in the lower tail, and you create a confidence interval around that sample, your confidence interval doesn't include the population mean, because you add and subtract your margin of error to get the confidence interval, like this. If the sample comes from the lower tail down here, meaning if it's a sample at the extreme low end, the entire confidence interval falls below the population mean. So it's actually this one right here. It falls completely below, meaning completely to the left. Now, what if the sample comes from the middle section? Then, like, what if our sample was of 30 people came from the middle area? Well, in this case, you create the confidence interval around the sample, and it does capture the population mean. The population mean will fall inside of the confidence interval in that case, as long as the sample came from somewhere in the middle 95%. So it will include the population mean because it came from the middle area. Now it says, what if the sample came from the upper tail of the sampling distribution? Well, if it comes from the upper tail, if it's a really high sample, and you create a confidence interval around your sample, you add and subtract the margin of error. The entire confidence interval falls above the population mean. It doesn't include the population mean because it's the upper tail. What if you're creating a 70% confidence interval? For example, what if I go to what if when I'm going to that z table right here, I don't use the 95% value like we did before. I use the 70% value, and I plug this in as my z-score. what's going to happen is by using this z-score, I'm going to end up creating a 70% confidence interval. And if you're creating a 70% confidence interval, then your sample still has to come from the middle area. But now, now the middle area has changed. Instead of it needing to fall in a middle 95% area, it now has to fall in a middle 70% area. So if you're creating a 70% confidence interval, the requirement is that the sample comes from the middle 70%. Any sample in the middle 70% will work, and you'll include the population mean. Anything in one of these tails won't include the population mean. So the percentage that goes in front of the confidence interval determines what the middle area is and what the two tails are. Notice how all of these add up to 100. What's the probability of getting a sample from the middle 70%? Well, probability and percentage are the same thing. So the probability of getting one from the middle 70% is a 70% probability. And 70%, if you write it as a decimal, becomes 0.70. I told you that if you create a 70% confidence interval, your sample has to come from the middle 70%. Otherwise, it's not going to work. It's not going to include the population mean. And I also told you that there's a 70% chance, there's a 70% probability of it coming from the middle 70%. So when we create a 70% confidence interval, we need for it to come from the middle 70% in order for it to work. And there's a 70% chance of that actually happening. That's why we have 70% confidence. So it's actually choice C. So I'm randomly selecting a sample from the population. I know that in order for my confidence interval to work, the sample that I'm selecting has to be one of the middle 70%. And I know that when I select my sample, I have a 70% chance of getting a sample from that middle 70% that I need to get into, which means so if I make it into the middle 70%, that's a success. And I know that I have a 70% chance of having that success, which means that I'm 70% confident that I did have that success that I'm talking about. So 70% confidence interval right up here, that means that you're 70% confident. If you create a 70% confidence interval, you're always 70% confident. So it obviously can't be one of these choices up here, because these don't say 70% confident. And we know that choice D isn't correct because a sample from the upper tail isn't a success. Choice 24 is similar. If you create a 60% confidence interval, that means that you're 60% confident. So it has to be one of the choices that say 60% confident, which means it has to be C or D. How do we figure out which one it is? Well, choice D says that the sample has to come from the upper tail. We know that's not correct, because if it comes from the upper tail, the confidence interval doesn't include the population mean. It doesn't work out. So it has to be C. So right away we eliminated two choices. We knew it was C or D because C or D say 60% confident. And we eliminated D because a confidence interval, when you create a confidence interval, you have to get one of the middle. You can't have one of the upper or lower tails. What happens when you raise your confidence level? What that means is, what happens if you go to that z-table and you decide to use a z-score that allows you to have more confidence up here somewhere? Well, you do become more confident that the population mean is inside of the confidence interval. In other words, you do become more confident that the confidence interval was a success. So that's correct. The problem is, whenever you raise the confidence level, what happens is you're using a bigger z-score. Notice how higher levels of confidence have bigger z-scores. What that does is, when you calculate the margin of error, you're plugging in a bigger z-score. And what that does is it makes the entire margin of error become larger. And if the entire margin of error becomes larger, then what happens is, when you create the confidence interval, you're adding and subtracting by a bigger number, by a bigger margin of error, and the confidence interval becomes wider. So when your confidence level goes up, the z-score gets bigger, the entire margin of error gets bigger, and because of that, the confidence interval becomes wider. So you become more confident, but the confidence interval becomes wider. And when it's wider, it's less precise. It's less useful for narrowing down the population mean that you're estimating. But let's look at the margin of error formula for a second. I said you're plugging in a bigger z-score, which makes the margin of error bigger, and that makes the interval wider. But what if you use a bigger sample size? And what would happen is you're plugging in a bigger number for n. But what that does is that makes the margin of error smaller. So if you're plugging in a bigger z-score to get more confidence, what you can do is use a bigger sample size to counteract that. If you plug in a bigger sample size, it'll bring the margin of error back down again. So raising the sample size. By raising the sample size, you can increase your confidence and use the bigger z-score without having to make the interval wider, because the bigger sample size will shrink the margin of error. Number 27 is asking you to create a confidence interval again, but this time I'm not giving you a population standard deviation. I'm giving you a sample standard deviation. Notice the word sample right here. If it's a sample standard deviation, we don't use a z-table, we use a t-table. So we're going to have to use the t-table to get our value. Whenever you go to a t-table, you have to subtract the sample size by 1. So 30 minus 1 is 29. Once you subtract it by 1, you get the row of the t-table. So 30 minus 1 is 29. we're going to go to the 29th row. Let's see if I have our t-table up here. Saying access denied. Hopefully I have it up here. Here we have a t-table. We go to row 29. It's n minus 1. It's a confidence interval question, so we can just go to whatever confidence we have. I think I said it's a 95% confidence interval, which would mean we use that column. So here we go, 95%, row 29. We get 1.699. That should be the answer. Oh, no. This, all 27 asks us to do is to create the confidence interval. So it's not broken into 3 separate questions like it was earlier. It's just one question. So what we do now is we have to get our margin of error. The margin of error formula is pretty much the same formula, as it was before. It just, what I mean is the steps haven't changed. All we have, instead of z, we have t, and instead of sigma, we have s, but otherwise the steps haven't changed. Margin of error population standard deviation is unknown. Meaning, what I'm meaning is when we don't have the population standard deviation and all we have is just sample standard deviation, we use this one. So I'm giving you I gave you a sample standard deviation. I did not give you a population standard deviation, so we're using this formula. The letter S means sample standard deviation. This meant population standard deviation. So let's plug in that t-score that we had, which was the 1 point. It was 2.045. Let's also plug in the sample standard deviation that I gave you. I told you it was 8.685. You're going to divide that by the square root of our sample size. Our sample size is still 30. We have 30 heights. So n is still 30. Once we do all of this math, right here, we'll have our margin of error. And you're going to be doing the same exact math that we did last time when we reached this margin of error. So do these steps over again, but with these numbers, you'll get your margin of error. And then once you get your margin of error, what you'll do is you'll add and subtract your, once you get the margin of error, what you'll do is you'll calculate the sample mean. The sample mean is just the total of these 30 numbers divided by 30. So you'll add the 30 numbers, you'll divide by 30, and you'll have your sample mean. What you can do now is do this. Sample mean plus margin of error, and then also subtract. Subtract the sample mean by your margin of error, and you'll get two answers. This will be the lower end of your confidence interval. This will be the higher end of your confidence interval. And then your final answer will be something to something. Depending on what two answers you get. I didn't give you correct choices in here, so we'll have to, your answer will be one of these choices, because I did this wrong by accident, so your answer will be something to something else. If you're creating a 95% confidence interval, you're 95% confident, the answer has to be D. In a real life study in which a confidence interval is being calculated, no population values are actually known, because you don't have data from the entire population. So the population mean can't be calculated, the population standard deviation can't be calculated. No population value can be calculated in a real study, which means we don't know what the population standard deviation equals, because if we wanted to calculate it, we would have to have data from all population members, which we don't have. Since we don't have data from all population members, and we can't calculate the population standard deviation, we use a t-score, which means that C is the correct answer. And for these other questions, I'll let you think about these a little bit longer, because I think that these ones are more straightforward. You just have to understand what all of the terms mean. These questions ask about my analogies. Remember that the null hypothesis is the absence of something. The alternative is the presence of something, or the existence of something. Let's see which ones I should talk about. Remember that a type 1 error happens if you reject the null hypothesis and it turns out that the null is actually true. A type 2 error is when you when you fail to reject, meaning you hold back from rejecting the null hypothesis, and it turns out that it turns out that the alternative is actually true, and the null should have been rejected. That's a type 2 error. I'll talk about this one. The p-value, the definition of a p-value is the probability of getting a certain outcome or a more extreme outcome, meaning a certain outcome or even higher, and it's also in a certain situation when the null hypothesis is true, which would mean that if we have this outcome, which is my computer freezing 3 times, and there's a point, that outcome has a p-value of 0.11, that means that that's a probability of the computer freezing not just 3 times, but 3 or more times in the situation of the null being true, because that's the p-value definition. So it has to be choice C.